Welcome to aminacademy.com. In engineering thermodynamics, let us discuss about its basic concepts. In broad terms, thermodynamics deals with the transfer of energy from one place to another and from one form to another. The key concept is that heat is a form of energy. Heat is a form of energy is the basic concept of thermodynamics corresponding to a definite amount of mechanical work. That means heat and energy work is interconvertible. Kinetic theory of gases. Assume that the molecules are very small relative to the distance between the molecules. The molecules are in constant random motion and frequently collide with each other and with the walls of any container which provide a pressure. Pressure exerted by a gas. Look at this, the closed container. Every body is made up of molecules. We know that. Depending on its nature and temperature, the molecules may possess translatory motion, vibratory motion, and rotatory motion about its axis. Each type of motion provides some kinetic energy to the molecules. Heat possessed by a body is the total thermal energy of the body, which is the sum of kinetic energies of all the individual molecules of the body. The temperature of your body is the degree of hotness or coldness of the body. Heat flows from a body at high temperature to a body at low temperature when they are in contact with each other. Modern concept of temperature flows from zeroth law of thermodynamics. That is, temperature is the thermal state of body that decides the direction of flow of heat. That means from higher, medium temperature to lower temperature. Now, temperature is a fundamental quantities of thermodynamics. Now, kinetic theory of gases, little detail we'll discuss about. Here, the founder of modern kinetic theory of heat by common consent is Daniel Bernoulli, but the credit goes to mainly on Clausius and Maxwell. Some postulates you have to take for a kinetic theory of gases. Gas consists of very large number of molecules. Each one is a perfectly identical elastic sphere. The molecules of a gas are in state of continuous and random motion. They move in all directions with all possible velocities. Size of each molecule is very small as compared to the distance between them. Hence, the volume occupied by the molecules is negligible in comparison to its volume of the gas. So, that means each molecule of a gas is compared to very less to compared to its total volume of the gas. There are no force of attraction or repulsion between the molecules and the walls of a container. That means with repulsion or attraction it won't work. Its nature, it randomly move. Collision of the molecules among themselves and with the walls of the container are perfectly elastic. Therefore, momentum and kinetic energy of the molecules are conserved during collision. That means it returns back. A molecule moves along a straight line between two successive collisions, and the average distance traveled between two successive collisions is called the mean free path of the molecules. The collisions are almost instantaneous. That is, time of collision of two molecules is negligible as compared to the time interval between two successive collisions. That means the collision of two molecules is negligible as compared to the time interval between the two successive collisions. That means from next collisions. We know that Avogadro number. Avogadro number is defined as the number of molecules present in one mole of a substance. It is constant For all the substances, its value is approximately 6.023 into 10 power 23 molecules substances. Now we'll derive a pressure exerted by the gas. You look at this figure. This is a three-dimensional box. That is in a three-dimensional space. Imagine a box is kept with a length L, cubical box. The molecules of a gas are in state of random motion. They continuously collide against the walls and the container. During each collision, momentum is transferred to the walls of the container. The pressure exerted by the gas is due to the continuous collision of the molecules against the walls of the container. Look at here. Consider a cubic container of side containing n molecules of perfect gas moving with velocity c1, c2, c3 up to cn as shown in the figures. A molecule moving with velocity c1 will have velocities u1, u2, u1, v1 and w1 as compared component along the xy direction. So suppose velocity c1 is having components of velocities u1, v1, w1 in xyz directions. Similarly, another molecule c2, c3, c4 like. Therefore, only x component of the velocities of the molecules is relevant for wall first, that is wall. First we consider that is x direction its collide. Now look at here. Since the collision is elastic, the molecules will rebound. Is rebound with the velocities u1 in the opposite direction. Hence, the momentum of the molecule after collision is minus mu1. Suppose the molecule having mass m and in x direction its velocity is u1, so its momentum is mu1, and in perfectly elastic collision, so it come back with minus m1 u1. That means final momentum minus initial momentum is called change in momentum. That is equal minus, my final momentum is minus mu1 minus mu2. Change in momentum equal to minus 2 mu1. During each successive collision on phase L, phase 1, the molecule must travel a distance of 2L from the phase 1. The phase 2, 1 and 2, it travels 2L because go and come back. Time taken between the two successive collision is, that is distance by velocity, that is 2L by u1. It's the time taken between two successive collisions. We know that a rate of change of momentum equal to change in momentum divided by time. That means change in momentum is rate of change in momentum is minus 2 mu1 divided by the time taken is 2L by u1. After simplifying, we get mu1 to L, 1 to over L. That means from one phase to that back phase. That is here, rate of change of momentum is this one. Now, force exerted on the molecule is rate of change of momentum is force. Therefore, you can write force. Force is minus mu by T general. Now, the component of velocity is u1, v1, w1 is considered here. Then, according to the Newton's third law of motion, force exerted by the molecules is force equal to mass into acceleration. That is Newton's law of third law of motion is every force there is an opposite, equal and opposite reaction. So minus mu12 over L equal to minus and minus become plus. So mu12 over L because it equal and opposite reaction. Force exerted by all n molecules, suppose Fx in x direction, these are first molecule, second molecules, third molecules, up to n molecules. So we are considering this is Fx direction, that is force on Fx direction. Pressure exerted by the molecule is equal to, we know force by area, that is Px equal to force on Fx direction over A, that is equal. We have to substitute these values, and here we get, that is F molecule M over L3 U12 U1 U22 U3 3 like it goes, that is, so it is in the x direction, pressure exerted in x direction. Similarly, pressure exerted in y direction is Py Pz. Since the gas exerts same pressure on all walls of the container, so all are equal, that is Px equal to Py equal to Pz, let it be P, generally P. Now adding all, that is Px plus Py plus Pz divided by 3, that average equal to P, and substitute the values Px, Py, Pz here, and we'll get P equal to 1 over 3 M over L3 into C12 C23 like this. So this it's not L3, it is L cube. L cube means volume, we can write it. Here finally we can get pressure is 1 over 3 Mn over V into C square. So therefore pressure we derived, pressure equal to 1 over 3 M into N over V C square. Where C is called the root mean square RMS root mean square velocity, which is defined as the square root of the mean value of the square of the velocities of individual molecules, that is C equal to square root of C1 to C2 3 like up to n values. So we got expression for pressure for the molecules gas in the container is this one, 1 over 3 Mn over V into C square. Now next concept, look at here. Next concept, we'll get it now. Kinetic interpretation of temperature. Kinetic here, temperature is the main concept of kinetic theory. Here V of the molecule is the volume occupied by the 1 gram of molecule of a gas, and N0 is the number of molecules in 1 gram of molecule of the gas, that is M equal to molecular weight. M is the molecular weight, that is equal mass of each molecule and number of molecules. Then P V will equal to R0 T, molar gas equation. This is a gas equation, P equal to RT. Now P we can substitute 1 by 3 M N0 average velocity is equal to R0 T. Therefore, here N0 is Avogadro number, R0 is universal gas constant, which is, we can write this one in the term of life. 1 by 3 can be written as 2 by 3 into half, that is becomes 1 by 3 m N0 average root mean square velocity, average square of the velocity equal RT, or you can write half m c square equal 3 by 2 RT by cross multiplying. Therefore, from this you can get C bar equal square root of 3 kT over m. This is some formula for average velocity. Now first is 3 kT over m, which is equal 3 R0T over capital M. From this you can write C bar equal 3 RT. Next, here this is there. In this, consider this R0, the given values are R0 equal universal gas constant, N0 equal Avogadro number, Avogadro's number. Next, R0 over N0, which is equal K, the Boltzmann constant. Therefore, we can simply write K over M equal R0 over N0M, which is equal to R0 over M. Then from here we can write R equal R0 over M, where R is a characteristic gas constant. R equal to characteristics gas constant. So far we discussed about basic concept of thermodynamics. In further videos we will discuss further about detail about the thermodynamics. If you have done, please subscribe our YouTube channel.